Hello, welcome back to the Bootcamp. Mass Eco, we move on to the third topic, partial differentiation. Okay. Upon going through the basic concepts, then we move on to the economic applications of partial differentiation. Okay, so this is now we move on to this type of function, say as a function of two variables, x and y, and then you have got a lot of real life examples. Remember, long run production output is a function of two variables, labor quantity and capital quantity. And also remember from your other topic in second year micro, utility is a function of two variables, quantity of good X consumed and or purchased, and quantity of good Y consumed or purchased. Okay. And then you have to know the following concepts. The first order partial derivative. So this term means you differentiate the function with respect to x. Okay. And then this other term means you differentiate the function with respect to y. So these are the two first order partial derivatives of function C. Okay, we can do this question. Okay, slide number 5. This is a relatively easier example. Then I rather focus on the more difficult example on slide 6. So this is the function, say as a function of x and y. You differentiate the function with respect to x. So this term, 3x cubed, would become 9x squared. You should remember the rule, you pull the exponent down. So 3 times 3 gives you 9. Then the exponent value drops by 1. So you have square now. And then this term would become 4x. This term, the x would become 1 after differentiation. So you have 10y here. Here you have 2x times 10, and then y, then you have 20xy. And then the last three terms don't feature x, so they all fall away. And then the next first order derivative, you differentiate the function with respect to y. The first two terms disappear because they don't involve y at all. The next one, the y becomes 1, then you still have 10x here. Here you have 10x squared, the y would become 1 after differentiation. This term becomes 5 after differentiation, then you have 12y here. Remember, you pull the exponent down and so forth. Then the last one, you will have 30y squared. Okay, when you have time, you can do this question at the bottom of this slide. Okay, and then more practices. Okay, you can do it on your own. And then we have got a few examples on the study guides. We rather derive first order partial derivative, but on economic application. So in other words, for this one, chapter 5, question 4, I simply rename say as total revenue. So total revenue is dependent on the sales of two goods, quantity of good X, quantity of good Y. Similarly, 4.3, say is renamed as total product. Total product is a function of two variables, labor and capital. So in other words, I rename X as labor quantity and I rename Y as capital quantity. So when you have time, you can go through this page. I think it is page 2 of the study guide. Chapter 5, prescribed textbook, chapter 5, question 4. Okay, and then we go back to the applications. Okay, we officially move on to the applications. Partial elasticity. Quantity demand of good 1 is dependent on 3 variables, per unit price of good 1, per unit price of good 2, and then income. And then there are 3 elasticities for you to calculate, and then you have to interpret the answers. Price elasticity of demand of good 1, cross elasticity of demand between the two goods, and then income elasticity of demand of good 1. And you need to remember all 3 formulas. They won't be given to you in the formula sheet. And then you have to interpret the answers. I'm going to stop for half a minute. You actually learn all these interpretation stories from your first year microeconomics. Okay, and then you can look at the questions I did on slide 10 and then try to do the practice on slide 11. And then I would only do one question. I think on the study guide I did 2 questions, but I will just explain one here. I think I can enlarge this a bit. Okay. You are given the equation Q1 is equal to 30 minus 2P1 minus P2 minus 0.02y. P1 must be given to you 7. P2 must also be given to you 10. Income is 100. 21.1 is easy, just substitution. Substitute these information and then you derive the Q1, which is 4. You must derive the Q1 correctly, otherwise the three elasticities would be wrong because all three equations feature Q1. Okay, price elasticity of demand of good one equals minus P1, you already know it is 7, divided by Q1 you derived just now, 4 times dQ1 over dP1. It means you differentiate this function with respect to P1. Then don't you get minus P here? Yeah, minus P. And then the answer is 3.5, which is greater than 1 in absolute terms, so elastic demand of good one. Then the cross elasticity equals P2 given 10 divided by Q1 4 you derived earlier times the dQ1 over dP2. It means you differentiate the function Q1 with respect to P2. Then you have minus 1 here. Okay, then the answer is minus 2.5. Then it means the two goods are complements. Okay. So it means when the price of one good drops, the quantity demand of the other good increases. So they move in different directions. So it means they are complements. The last one, income elasticity of demand of good one. This is the equation equals y 100 divided by q1 4 times dq1 over dy. You already know the answers here. First order partial derivative, so minus 0.02. Then your answer is minus 0.5. So it is an inferior good, meaning when income increases, the quantity demand of good one somehow drops. Inferior good. Okay. Then the next part is unconstrained optimization, and then there are some explanations and an example on the slides. But I want to focus on the explanation on the study guide instead. Because for unconstrained optimization, the focus would be on maximizing something. Yeah. So in this bootcamp, we focus on unconstrained maximization. Okay, say as a function of two variables, x and y. Okay, you need to first find out quite a lot of derivatives. The two first order partial derivatives, dz over dx, dz over dy, and then second order derivatives. So this term means you differentiate the function with respect to x twice. So this is your second order derivative. And this one, it means you differentiate the function with respect to y twice. So this is your other second order derivative. And then this one, you see dx, dy at the bottom. It means you differentiate the function with respect to x, and then afterwards you differentiate it with respect to y. Okay? And then at the critical points or at the turning points, both first order derivatives are equal to 0. Then you can make use of simultaneous equation to solve for x and y. Okay, and then the next condition for the maximization of say, these are the conditions for the second order derivative. This one with respect to x, negative. This one with respect to y, negative. And then this whole thing actually, just really carefully, it must be positive. Okay, then we can move on to do this question. Okay, real life application, profit is a function of two variables. So I just rename say as profit. Okay, we must derive the first order derivative. So 24 minus 2x minus y. The rest falls away, they don't feature x. So this is the first order derivative with respect to x. And then the first order derivative with respect to y, I think these two terms falls away, they don't include y. This one, the y would become 1 after differentiation, but you still have minus x here. Then minus 4y plus 33. Okay. And then I derive the second order derivative. Okay, with respect to x, it means for this one, I differentiate it one more time with respect to x. This is why I get minus 2. And then this one, it means I differentiate the function with respect to y one more time. This is why I get minus 4. Happy with that? And then for this one, it means I have to go back to this first order derivative and then I differentiate it one more time, but this time with respect to y. This is why I have minus 1. Okay? And then at the turning point, remember the condition, both first order derivative, which we already derived, equals 0. Then you can look at the answers. We make use of simultaneous equations. We can derive x equals to 9 and y equals to 6. And then we check the second order condition. So let me stop for 30 seconds to see if you can understand. The first two must be negative, which is the case. And then the last one, this whole equation must be positive. So I think we meet all the requirements. So meaning indeed when x is 9, y is 6, it would really lead to maximization of profit. And then you just finally substitute x equals 9, y equals 6 to find out this maximum profit amount, which is 164. So let me stop for 20 seconds for you to go through all the answers. Okay. Then we move on to constraint optimization, and then the first type of questions would be on consumption. So utility is a function of x and y, and then we make use of first order derivative to derive marginal utility of x. It means you differentiate u with respect to x, and the marginal utility of y means you differentiate u with respect to y. So remember, this utility function is also your indifference curve. Marginal rate of substitution is actually downward sloping change of y over change of x, which is actually equal to negative marginal utility of x divided by marginal utility of y. Budget line, this is the equation. Okay. Budget constraint equals per unit price of x times quantity of x plus per unit price of y times quantity of y. The slope of the budget line, negative px over py. At equilibrium, the budget line is tangent to the indifference curve, and then this is the relationship, and then we usually take absolute values. This is why we remove the negative sign on both sides, and you'll be asked the questions to find out the x, y quantity, which will maximize utility subject to the constraint. This is why we call it constraint optimization, subject to the budget constraint. Okay, this is the graphical illustration. And then I'm not going to go through this example on the slides, very comprehensive. So maybe I will just do one questions. Okay. Let's do this one. Question 8, chapter 8. Okay. Marginal utility of x. So it means you differentiate u with respect to y. So you see I pull the exponent down, then 3 times 0.8 gives you 2.4. Then x, the exponent reduced by 1, and then you simplify into this. Then similarly, this is how I derive marginal utility of y. And then the slope of the indifference curve in absolute terms, marginal utility of x divided by marginal utility of y. You just have to simplify a bit until I get 8y over x. Okay. Then the slope of the budget line in absolute terms, px over py, which is 16 over 4. Yeah, the budget line equation. Yeah, 16 over 4, which gives you 4. At equilibrium, these two terms are equal to each other. Then you start deriving the relationship, x equals 2y. This is the budget equation. Now I substitute this relationship, x equals 2y, into the budget line equation. You eventually solve for y equals 48. X equals 96. Then the last thing you have to do is just to substitute x equals 96, y equals 48 into the utility equation to find out this maximum utility amount, 170 point something. Okay, then in the next video, we move on to the other types of constraint optimization question, which relates to long-run production.